you have unmuted yourself. Okay, and are your slides in presentation mode at the moment?
I'm gonna have to put them in once I get them sharing.
Okay, first of all, I think Alex, you are there, right? Can you introduce Anthony, please? And then invite him to come to make the presentation, please.
Okay.
Rest of us, let's mute ourselves.
Yes, Anthony, I hope I pronounced it right. Gwartney is
right.
a business development manager with 40 years experience in operations, sales, and design of oil and gas, onshore, offshore, deep water completions. Anthony started his career as a completion pumping operator, then was promoted to pumping assistant, and ultimately completions tool specialist. He had various roles during his professional career, including pumping field supervisor, international completions rotator, international operations coordinator, product line manager, international multilateral specialist, Gulf of Mexico sales, product line champion, project manager, deep water, Gulf of Mexico, and business development manager, deep water, Mexico. Anthony's experience includes onshore, offshore, deep water, oil and gas developments in 22 countries. He's now North America Trinidad Business Development Manager, serving as liaison to our US-based clientele, which include the local majors such as Shell, Chevron, and BP, and expand to Trinidad business operations as well. A few of Anthony's career highlights include many firsts. First 15K SI frac system for NIFT Deepwater Project Gulf of Mexico. First deepwater project multi-zone single trip system installed in the lower tertiary Gulf of Mexico. First installation of pressure actuated fluid loss devices for major operators in the Gulf of Mexico. Project manager for first deepwater subsea intelligent well completion in Gulf of Mexico. Installed the first level 3 multilateral completions in Venezuela. First rotating completions project coordinator. First completions job coordinator, in addition to other career achievements. And without a further ado, I will let Anthony Gwartney take over. Anthony?
Thank you. That was a little more than I expected all that, but that's fine. Hopefully this presentation isn't as controversial as Shabazz, so we'll see. I wanted to talk today about ICDs and AICD technology. So just kind of walk through the technology, how it works, what the applications are, and where we use it. I guess everybody can see my screen.
Yes, we can see it.
Yes.
Did you put it in presentation mode?
Yes.
Okay, we can see it.
Yes, okay, great. So again, I just want to thank everybody for allowing me to present today. It's a real pleasure to be with all of you. So virtual presentations are a little awkward for me, so we'll see how it goes here. The first thing I want to talk about is passive and autonomous ICDs. So we've got two types of ICDs as we look at them in two different applications, if you will. The challenge typically is in horizontal wells, although they can be run in vertical wells also, but predominantly horizontal wells with a thin oil rim, high permeable formations or fractures, and non-uniform saturation. And then we're looking for annular flow and cross flow. And of course, the main issues are early water and/or gas coning, which will create hot spotting and screen erosion. So we're trying to combat all of those things when we look at controlling the flow into the wellbore. And so when you look at this, typically what happens with these high K homogeneous zones, we'll get an even flow in, and then this coning effect will happen with gas or water. And some of the ICD devices you see below, some nozzles, tubular type, helix type, labyrinth, or hybrid type. So there's a lot of different ways to run the inflow control devices and types of inflow control devices. But the main idea of these devices is to create additional pressure drop to balance the production flux, but not restrict the unwanted effluents once they break through. So the key principles of a passive ICD is that they can be used both in producers and injectors. They're generally run with sand screens or short filter element to prevent plugging. So we'll see it a little later on, but we need to have some type of either filter media or certainly a debris filter if sand control isn't required. And then again, as we go through this presentation, we'll see how compartmentalization is very, very important in this technology and the effect of it. So to be effective in providing proportional inflow, the average pressure drop across the ICD must be approximately equal to the average drawdown on the reservoir. And so that's when we talk about these passive ICDs or the nozzles. As we move into the autonomous ICDs or the AICDs, you'll see the difference there in the two devices and technologies. So this is basically showing what this nozzle type ICD looks like, and it's a function of pressure drop and density rate squared. So basically, it's just choking back through your nozzle size, and you factor that in to choke back those fluids coming in, and then hopefully create an even flow across the reservoir zone into the well. And so the solution with passive ICDs, if one of these high K homogeneous zones, you're getting an even flow in. And so you can have a limited effect there with ICDs because you're just choking everything out. But ultimately what you're really looking for is that heterogeneous zone where you have a dominant flow area into the wellbore and it allows you to control. But as you see on the bottom, the key part is when that water or gas comes in, it really will just dominate the flow going into the wellbore. And what we see a lot with a lot of operators is that point, if they have high water cut, 95, 98%, they just start trying to pull on the well harder and just chasing the oil. So they increase their total liquid volume, trying to get more oil pulled up in there, but it's always a challenge because at the end of the day, whatever water or gas you produce that really is not what you're after, you have to deal with that on surface. And so it becomes kind of a time, money, and effort situation dealing with those fluids that you're not trying to get out of the ground. So when we talk about compartments, that's the key to this technology and these devices, is your ability to really control the flow. So you see the green arrows coming in is your production coming in, and you can see that once the water, in this case, breaks through, or it could be gas, it just dominates the flow. And typically in these horizontal wells, we see that breakthrough closer towards the heel. And so again, it's going to dominate the flow. Now you're chasing the oil more towards the toe of the well. If we create compartments, it allows us a little more control on this flow coming in with passive ICDs or AICDs. So you're able to control it. The fluids are not jumping over. You have a little more control, so you can get the oil out of closer to the toe and the heel of the well while controlling those areas where water's breaking through. So when we talk about compartments, the key is really the more compartments you add, the clearer, more focused the picture comes in. And then it also becomes a balance, because you can see at the bottom where we have several compartments in there. Sometimes it just doesn't make sense to do that. So you have to really balance it. And so the question becomes, how many compartments do we need? And of course, there's a lot of things that weigh into that determination. It could be the heterogeneity of the rock, and we're looking for the permeable fluid saturations. There may be natural compartmentalization of the reservoir, mechanisms of breakthrough of the unwanted effluents, risk of aversion drilling completion. So how many of these swell packers are you going to run in to create these compartments? And then, which is not on this list, it may be an economic driver, because at some point you have to weigh cost versus theory, if you will. So when we look at passive ICDs and where are they placed, so how do you run them in the ground? And typically they're run with a standard screen joint. You can run them in standalone screen environments, typically when you're running horizontals. There have been some run with horizontal gravel packs. A lot of times we see them as standalone options, and this particular graphic shows a wire-wrapped jacketed screen or even a premium screen you can run. And so the flow path is coming in where you see the blue areas, oil or water, whatever the case may be, coming through the screen, up the mini annulus that's created between the non-perforated base pipe and then into the device itself, and then up into the production flow. So that's how we're controlling it. And you can see the nozzle up here in the left-hand corner. But here's kind of the kick or the caveat for ICDs, passive ICDs, are those low Reynolds numbers. So once water or gas breaks through due to the higher mobility in the reservoir, the ICD completions will result in higher water or gas production. So you're going to choke it back for a short period of time, bring the well on, allow the oil to come in. But once the water or gas gets there, there's no ability to stop that effluent from coming in. At the end of the day, it's just a small orifice, which is allowing you to, hopefully in the front end of the well life, get a little more even production coming into the well bore. So when we look at it and move on to autonomous inflow control devices, these have a little more flexibility and they're an active device. So you see the picture, this is ours. There's many AICDs on the market, and there's a lot of different devices and they function in different ways. The particular one I'm showing you is one of our devices, which just has a floating disc. And it regulates flow of fluids, primarily used in horizontals, multilateral, other advanced well architectures. So we can run them, we've run them in vertical wells as well and retrofit environments, but predominantly horizontal wells. And the AICD is capable of modifying its flow control characteristics autonomously in response to fluid properties to exclude the unwanted effluents. So that would be water or gas. And this device, although it differentiates between the three fluids, it is active in water or gas. So if you have a combination of those fluids coming in, it will choke them both back. And we'll see a little more of that as I move on in the presentation. The device demonstrates a significantly different response in pressure drop versus flow rate performance as a function of the fluid type. And we'll demonstrate that again as we go through. And you can see the picture kind of in the lower left-hand corner depicts a horizontal well where we're running, creating these compartments so we have a little control of the fluid. And one of the things you see on the device is the inlet is a single port coming in on top of the disc, and then the bottom of the disc where it's flowing out is multi-ported, or we call that the shower head on the back side of the production side of the valve. So this particular device works on three forces acting on the disc. There's a force down due to momentum, a force lifting up, a hydraulic lift, and then a force down due to viscous drag. So there's an airfoil created, Brunelli effect, if you will, as the lighter viscous fluids come in. So when you see the picture on the left top, that's oil coming in, disc all the way down, fluid oil coming around the top of the disc and then out that shower head piece. As water or gas comes in, lower viscosity fluids, higher velocity, lift that disc. And just to go through it again, talking about the higher viscosity fluids, pushing the disc away. You can see it in the picture there, disc is all the way dropped down. As the water comes in, the velocity increases and lifts the disc or moves the disc away from the bottom, choking back the fluid. And then of course, gas will pull it back even more. And so we describe it as choking because this disc never fully closed. So it will still produce water or gas, but in a much limited rate to allow oil to come in through the other compartments that you've created. And one of the nice things about this device is that if oil works its way back around to the front of the device, then the device will go back into that production or that drop down mode and allow the oil to produce. And as water or gas comes back to the valve, it'll start its choking effects again. So just a little graph showing the single phase testing that we've done, and of course we've talked about it again. Chokes water and gas, low viscosity. It opens for the oil, high viscosity. The thicker the oil, the easier it flows. And so you kind of see in this highlighted green area, pretty much the sweet spot of the valve and how it works. And you see that there's a low differential or pressure drop across that valve as it's producing the oil and then choking back waters or gas. And again, the beauty of all these devices is they're similarly located in screen joints, and there's a variety of, and we'll look at it later, but there's a lot of flexibility in how you can run these, whether it's in a premium screen or a wire wrap screen, or we can even use shrouded joints if sand control isn't there, and we have subs if no sand control is required, but we certainly want a debris filter at a minimum over these devices to protect them. But again, the flow comes in the same way. It's located in the same position as an ICD. Flow coming through that screen joint, up through the mini annulus created between the non-perforated pipe and the jacketed screen. And then the lower zone depicts some compartmentalization, and you can see the red piece coming in, where it's coming into that compartment, being controlled by the AICD, and the other compartments allowing flow to come into the wellbore. So some myths and realities about AICDs. They're not downhole separators, so what comes in must go out. So whatever's coming in that well, we choke it back, hold it back, and at some point, those fluids will jump across the compartments that we've created. The idea is twofold. One, that you don't need to pull on the well as hard as previously when you're not running this technology, as we talked about, chasing that oil out at 95% water cut. Some of these operators are pulling 3,000 barrels a day to get 200 barrels of oil out. And in this environment, maybe you're pulling 1,000 barrels a day and you're getting 400 barrels of oil out a day. So it allows you to not work the well as hard. However, at some point, it's still going to water out or gas out or whatever. But the devices hopefully help you produce more oil longer and extend the life of the well. But here's the big one. AICDs cannot change water to oil. We would probably really have something if we were able to do that. But so far, we're not able to change water to oil. To improve oil production, though, and this is a key piece we talked about earlier, there must be a variation in the oil saturation or oil cut along the length of the wellbore. So like we talked about with the homogeneous wells, if you've got even water flow or gas flow coming into the wellbore, AICDs are really not going to work because it's just going to choke back all the way across the length of the zone. And again, that kind of what goes comes in must go out. And if the whole length of the well bore is at 90% water cut, the AICDs cannot make an improvement. And again, to reiterate, the AICDs react on the properties of the fluid passing through them. There must be a significant difference in viscosity properties. So these devices, the AICD devices, work on the higher viscous fluids. If you're in a light oil environment and you want some choking, that may be a case where the recommendation would be a passive ICD, because the AICDs really are not going to differentiate enough between the lighter viscous fluids and water, as an example. And AICDs can be an insurance policy on a reservoir performance uncertainty. So a lot of times we can install these in the early life of the well, and it's just going to guarantee you've got that even well flow in. And when we look at some of the case histories, I can talk to you about some of those wells where our projects where they've been a really enhancing technology to what the project started out at and what it is today. And as you can see, the little graph doesn't show it very good. Maybe you can't see it, but we have run thousands of these things and hundreds of wells. So more than 280 wells. I think these numbers are probably low, probably closer to 60,000 of these devices run globally. The U.S. is a little slow getting in. We're breaking through a little bit in some of the lower 48, some stuff out in California, and we've got some stuff out in West Texas right now we're looking at, but it's been slow. But the rest of the world has really adopted this technology. And so one of the questions we get is about erosion and plugging and you know, what happens if you get some fines coming through, or in your case where mud's coming through, are these devices going to plug or erode? And so we've done some extensive testing on these devices, some erosion testing with silica dust, and really met the standards. Equinor or Statoil, back in the beginning, they developed the AICD technology, and our company just really modified it and improved on it. But we went through some stringent testing based on their criteria and requirements. And so this is just a quick showing you that the test, the wear limits, all the materials, and again, this was a Statoil test with the silica dust. And 10 years, determined 10 years, 30 bar, and you can see very limited wear. And again, the plugging is a big one because you have a lot of muds and different fluids coming in. And when we look at the ports, the first thought is, wow, these ports are not very big, the entrance port. Are they susceptible to plugging? And I would just tell you, we satisfied all the plugging tests. And at one point they tried to load up the solids, trying to get the devices to plug, and they really never could get it to plug. So satisfied all of those mud plugging tests that we've run. And then track record, just to talk about some of the ones. And again, this is the Statoil Troll, which is probably the biggest highlight of the technology. The Statoil Troll project started out as, I think, 5 originally vertical wells, and they had a thin gas cap, and so our thin oil layer with a gas cap. And so they ultimately drilled horizontals into the thin oil rim. But what happened was the gas just immediately started to break through. And passive ICDs were starting to enter the industry at the time, and they employed some ICDs in these wells and did have some improved performance. They were able to hold back the gas a little bit longer than not doing anything, and they were doing open hole gravel packs, passive ICDs. Then they started to employ, and this one probably jumps ahead of the story a little bit, but I will just tell you, and maybe I'll go ahead one and then come back. Some of the testing that they've done with the AICDs is that once they developed and started to run them, they found out that the AICD wells were producing in 9 months the same as the ICD wells did in the life of the wells. And the AICDs showed a stable production profile while the ICD branch had been choked. So they ran some multilaterals in one AICD, one ICD, and that's really what they were doing to try to compare the two technologies. And again, when they looked at their experience, and these were the SPE papers written for these projects, following the successful trials of the AICDs, they installed them in all the troll wells. They didn't have any additional complexity or risk to the completion or production of the well. So everything was just as they were doing. There were no added risks run. However, the AICDs enabled the troll wells to be produced at higher rates for longer consistency, resulting in 15 to 20% more oil production, which, as we all know, especially in this environment, is huge. And now when I go back to this particular schematic, if you remember, I talked in the beginning that they were drilling single lateral horizontals and gravel packing them. Well, after installing AICDs and they were getting this even flow into the well, they were not moving sand, they were not creating hot spots or eroding screens, and they really determined that the AICDs were helping their sand control problem as well. So because of that, they're now drilling these trilateral completions, all standalone screen, no gravel packs, all employing AICDs, and have really increased the production of the field. And again, this field started out as a 5-well project, and it's been going on well over 10 years now. So very, very successful, and a lot of it is because of, in the early stages, ICDs, and then the advancement of the AICD technology. So one of the things that we look at, and questions come up, well, okay, how many devices do you run? Where do you put the compartments? How do you determine all of that? Are you just, saying, hey, run 2, 3 here, create your compartments? No, we're not doing that at all. What we're doing is we're running through everything is going to go through our subsurface engineering group. So the first step we would do is we're going to gather as much information as we can from the operator. We need to define some AICD coefficients based on fluid properties, what the produce coefficient is specific to the fluid. So we want to look at all those well environments and the well architecture, and then we'll develop a problem statement, and we'll run all our net tool simulations and other simulations, and then create that opportunity statement and identify the solution. So one of the things that we do after that, we'll sit with the customer and we'll evaluate that and put together a value estimation as well. And we like to look at it as most operators, we want a return on that investment in 6 months. So it's great to say, we can install all these devices and compartments, but if it doesn't make economic sense, then it makes no sense at all. So that's part of the piece of weighing how many compartments you create versus the economics of the well. Kind of, is the squeeze worth the juice, so to speak? And so then the solution and refinement and selection. So that's where, after meeting with the customer, the operator, we can define that and tweak that down to what makes the most sense. And this is just an example of something that we would do in summary recommendation to look at the base case. So what have you been doing historically on the top? And if you can see some of the water rates and the total liquid rates, and in this case, up to 475 barrels a day in this particular well. And then you look at the water cut going from 42%, 42.8, all the way to 99% water cut. And you can see it's happening relatively quickly. When we model the AICDs, and historically we have track records that show this as well, you can see that even with the same total liquid rates, the oil rates change. So we've just displaced the water rates with oil. So we're choking back the water, allowing more oil to come into the well bore, and extending the life of the well a little bit longer. So you can see in the beginning, that's a little bit better. You know, I don't know if it's enough to make a difference, but as you go further on through the life of the well, kind of in that mid-range of the well, you're really getting a lot better production and control of the well as you're bringing in the oil. And we've had some customers that have told us once the water comes in, it comes in so hard and they're chasing it, at some point they're either cutting the screens, or if they're running slaughter liners, they're cutting them, and these wells are shut in within a month. So they might not even make the life of the well that they're hoping to get. And so in summary, the AICD summaries, they're proven to increase oil production by controlling water and gas. The performance is fully delineated using multi-phase testing, and that's used to generalize the performance and the coefficients used in commercial modeling software, so the net tools we saw. The technology is qualified for robustness during deployment and life of well operation. So we saw all of the testing that's done to qualify these devices. And it can be readily configurable within the completion without impacting completion functionality. So that's key. It really doesn't increase any risk in what the operator is doing, especially if they're running standalone screens. These devices don't change that at all. You're picking them up and running them similarly to a standalone screen. We did talk about zonal isolation, and the compartments are created, and you have some options there. And that's what I like about this technology, these types of completions. You do have some flexibility and diversity on how you set up the completion. So you can run it with standard swell packers, and in this case, maybe you're running on a 20-foot joint with a 5-foot element, but you also have the ability to run these swell sleeves. And I like the swell sleeves because they'll slide up over a blank joint of pipe, and you can position them anywhere that you determine you need them. So it allows you the flexibility to make those changes on location. If once you drill the well, you see some washout areas and you say, I want to move my compartment up one place or the other so it's more effective, or maybe that washout's longer than I anticipated, so let me stack a couple of these sleeves to make sure that I create that compartment. So you have some options in the compartment creation with the swell products. And then ICDs, one of the things I always recommend when we run ICDs, because these are production valves, and as we talked about, that base pipe is a blank base pipe or non-perforated base pipe. So you only have the ability to take production in. A lot of these wells later in the life, they'll want to do a solvent treatment or an acid treatment, something like that. So typically what we'll recommend is a bypass valve, or in our case, we call it a flow check injection valve. And so what that allows you to do is pump out of these valves and into the reservoir. And so you're going to run one of these devices in probably every joint where you have an AICD. And again, we'll model that too, whether we need 2 or 1 device in each one. But it just allows you to have the ability to pump out of the zone. And these devices are set up so that you have to overcome a force to pump through them. So they won't just inherently open up. You'll have to apply 200 PSI or something per valve to get that disc to lift off. And one of the things you'll see in a lot of these devices, they're all similar in design, which makes it easy because, again, when you look back at how the screen joints were set up with the AICDs, the whole tap, the whole size is exactly the same for this device. You're just going to tap another hole, screw it in the joint, the housing to cover it, everything is the same. And another option in the completions is, again, we talked about, you can go with premium screens, direct wrap screens. You can use the debris filters if you're in a non-sand control environment and you just want a shroud to go over them. We also run, I think I mentioned, in retrofit. The retrofits where you have maybe a cut screen or a cut slotted liner, really with those, a lot of times what we'd like to see is if you're going to run, say, a pre-perforated liner and some swell packers to create those compartments. And that'll allow you some control in the initial part of the well, but then if you need to retrofit, we can run inside of those. They lose their effectiveness if we don't have that compartmentalization out in the reservoir phase. You'll get a little, they'll help a little bit, but obviously that fluid's going to jump outside the perforated pipe or screen. And then again, we've got the different subs and compartmentalization as we talked about. And this is just a quick look at what we did up in Canada with the heavy oil retrofit and these small subs. So you can see that in some environments where economics are tight, and these wells in Canada, we're not big producers. However, they were shut in. A lot of these wells were shut in. And so this technology allowed them to put these wells back on production and get a little more life out of those wells and a little more production out of those wells, which was very beneficial to that customer. And again, just real quick to show you that many of these devices are on the same platform, if you will, whether it's the nozzles or these disc type devices that we see. And I think I have a little more time, so I'll go through another one, which is a dual choke when we look at EOR for heavy oil and some of the cyclic steam stuff and how these devices can benefit you there. So just a quick example of a cyclic steam stimulation. The idea is you inject the steam into the vertical part of the well for months, so you're injecting the steam, and then you produce well until it cools and repeat the process. Part of the problem in doing that, as you can see here, we have no control where the steam goes. So the challenge is that unequal heating results in inefficient production. You know, how do you optimize the steam distribution to get the best heating of the reservoir with variable permeability, shale barriers, perforations, etc.? How to allow for the unrestricted oil production? So the solution is the inflow control or dual choke. So just looking when you go into the production mode, when you inject it that way, you can see that you get dominant production from one zone or the other, and you're really not effectively treating the reservoir and getting the production results you'd like. So in doing that, the same, if we install these dual flow valves, dual control flow valves, it allows you to pump out and have a little control and get even injection into the reservoir. And conversely, you can treat it evenly. And then when you go to produce, you should get equal production out of all those zones. So you've maximized the steam injection or the steam stimulation of those zones. And so these devices, again, you see it on that same platform. And so the beauty of this dual choke injection is that while injecting, you're just going through the port. And so you can see the disc here in the upper left depiction of it. That disc lifts up and closes off flow so that you can only come up through the center. So that's injecting out, it becomes really an ICD. And as if you remember in the beginning, we talked about ICDs being used either in producers or injectors. So effectively, this device becomes an ICD for the choke injection or the steam injection portion. But when we go into production, it acts more like an AICD in the sense that the disc moves away from the port, allows the flow to come down the sides and out the bottom of that shower head device that we talked about earlier, and it goes through a much larger flow area around the disc. And again, it shows you it's located similarly in relation to a joint that's shrouded, that the AICDs, the ICDs, the bypass valves, all of these are similar. So it really does not change what the operator is doing as far as completion, if they're running standalone screens or even if they're picking up slotted pipe and running them. Shrouded subs are not much different in doing that. And so that's all I have.
Alex?
Okay, we do have a few questions here. The first one here is from Salim. On what principle AICDs are built? What viscosity differential it has to have with water to be able to differentiate between water and other fluids?
Yeah, we're looking for somewhere around 13 centipoids or higher. So the more viscous oils, and that's where the work, as I said before, if you get into the lighter oils, really you're going to end up more with a passive ICD as a type of a device that can help you control in the front end of the wells the water or gas production.
Okay, our next question here is from M. Usman. A higher drawdown will pull water harder. Can you model this in NetTool?
We do model it, and that's one of the things that's kind of a paradigm shift for the operators, because when we're modeling and looking at it, and they say, oh, but you know, I need to pull 2,000 barrels a day on these wells, so I need to model that. And we say, no, hold on. You don't need to pull that hard on the wells because you're holding back the water. So it's a little bit of a paradigm shift in that respect. But we do model all of those drawdowns on the wells and so that they can realize the production rates that they're looking for.
Okay, our next question here is from Francisco Pineda. Do any of the ICD type presented have the flexibility to close and open at will?
The ICDs don't. You know, they're really just ports, if you will. You know, they're just ported devices that go through, so they're just choking. I guess that in some cases, we've mounted them in sleeves, so a housing with a sleeve where you can open or close a mechanical sleeve to shut on and off that device. However, the ICD devices themselves do not close. We do have some devices built on that same AICD platform, which we call a flow fuse, and that particular device is really more for injectors, where you've got one area of that zone that you're injecting that is really taking the bulk of the fluid. And typically with that device, we'll run it in combination with a couple of ICDs. And so once that zone starts to reach a certain velocity over production, the device will just close. So a little different than the AICDs that choke, this flow fuse will just close and shut off that flow. And now you've minimized the flow just going out the ICDs so that you can get an even production across the zone length of the reservoir length.
Okay, we got another question here from Doug. Thanks, Tony. Excellent presentation. Any thoughts on the longevity of ICDs and AICDs?
Yeah, I think both of them have you know, long lives. ICDs, I would say that typically what happens with the ICDs, although they may have a 10, 15, even a 20-year well life, usually those wells, because they're not choking back water, usually those wells will water or gas out long before the device has any issues. With the AICDs, we've done testing, as you can see with the erosion, you know, up to a 20, 30-year well life and modeling. So that's what we're looking for. We're trying to get the full well life out of these devices, and so far we've been very successful.
Thanks, Tony.
Okay, that's all that we have.
Anthony, can I ask you some other question, please?
Sure.
You mentioned AICD cannot differentiate between light, less viscous fluid and water. If that is true, in that case, it means AICDs work on a principle of multi-phase fluid flow. Is that correct?
Yes. Yeah, so we really are differentiating between the viscosities, right? So the heavier viscosity fluids, you know, the three forces that I talked about. So the heavier viscosity fluids just push the disc away from the port, allowing that flow to go over the top of it and out what I described as the multi-port bottom, or that shower head bottom. And as those lighter viscosity fluids, either water or gas, come in, then the velocity of that fluid passing by the disc increases, and that Bernoulli effect kicks in and pulls that disc up towards the entrance port, choking back those fluids. And again, throughout the life of the well, that disc may change positions multiple times. As oil comes in, it'll push it away. As the viscous fluid comes in, as water or gas comes back in front, it'll choke back again. So that's one of the things when we talk about it being an insurance in some of these completions, is that we're not saying, hey, if you install this, you're going to choke off that section of your zone or your well. We're saying, no, if you run them across the interval length, you're going to have control at all of those compartments that we've created. And if at the heel we're choking back early in the life of the well, but oil comes to the heel, it's going to open up and let the oil in and then choke back as water or gas comes. What we're saying with the viscosities is the lighter viscosity fluids, those velocities kind of get closer to water, and it'll start choking back similarly to the effects of choking back the water.
So what is the main differentiation between AICD and ICD?
So ICDs really are just choking devices, right? They're just ports, you're just nozzles that you're installing in, and you're kind of determining what kind of choke you want all the way across that reservoir. So the ICDs are just nozzles that you're installing in, where the AICDs have a little and ICDs don't differentiate between fluids. They just choke everything back.
Oh, I see. Okay.
But the thought with an ICD is, if you can choke it all back, the water's not getting in front of you and just coming hard in the early parts of the wells. You're hopefully choking everything back and getting a more even flow into the wellbore.
So what would be the, in terms of price differences, what would be the price differences between ICDs and AICD?
ICDs are obviously less. I mean, it depends on how many devices you're going to run. Are you going to use some of those bypass valves or injection valves that I talked about? Are you going to run these devices on premium screen, wire wrap, direct wrap? Are you going to use a shroud? And how many compartments well, the compartments would be the same. But so that's really some of the beauty of this technology, is that you have that flexibility to fit the different well environments and economic environments.
Okay, so having said that, that means the AICDs must be much more expensive than ICDs, right? Because of its specialization.
Yeah, they're more expensive. I don't know if you'd classify them as much more. Again, the screen is really the driver on the price, what type of screen you're going to run. However, I'd say they are more expensive, but I guess at the end of the day, the
usefulness, right?
Yeah, and then the return on that investment is much higher.
Benefit that you earn out of it, yeah.
Yeah.
Thank you so much. Yeah. Alex, any other questions to Anthony? Alex, you are muted. Alex, are you there?
Yeah, sorry.
Go ahead. Are there any other questions to Anthony at this point? Either through chat or by unmuting, you can ask other questions to Anthony. No other. In that case,
just one question. I'm sorry.
Yeah, go ahead, please.
Hey, Tony.
Sure.
Is there any limitation as far as how many AICDs you can run in a well, horizontal, or what would be, and with that, what's the maximum amount of ICDs that you have run?
I think typically we're looking at lateral lengths of plus or minus 1,000 foot. Although I know we have some installations over 2,000 foot laterals, maybe more. I don't want to misspeak here, but there might be some longer than that I'm not aware of. Usually the driver is really the production. What kind of production are you looking for? So we look at, and the other piece is when you're creating the housing. So you could put multiple devices in that housing that I showed, up to, I think I've seen 4 AICDs per joint with a bypass or 2 bypass valves. So you're able to do that. Usually we're looking at, on average, probably 2 AICDs per joint or per section, if you will, whether it's a sub or a full screen joint, and possibly 1 bypass valve or flow check injection. And I always recommend that just because it's, you know, if you don't have it in there, you don't have the ability to pump that solvent job or acid job later in the life of the well if that's something that you think you might need to do. You're kind of handcuffed right in the beginning. So it's a small cost and a little insurance to give you some options later in the life of the well.
So, Anthony, having listened to your presentation, do you think these AICDs would anyway work better in a heavy oil environment than in conventional light oil environment? Or
yeah, so that's kind of what I said. So in the heavy oil environment, AICDs, really, that's kind of their wheelhouse, if you will. Light oil, we'll recommend the passive ICDs, the nozzles, just because of you're not going to get the differentiating between the viscosity of fluids of water and oil, the viscous oil, light viscous oil. So, and that's one of the things with the modeling that we do. You know, I've been, especially with TENDEKA since I've been here, I've been real happy to see that sometimes we go back to our customers and say, sorry, this isn't the application for that well, because you're just not going to get any benefit, especially those wells where you're getting even water flow into the wellbore. We really can't help you there because we're just going to choke everything back.
Mm-hmm. What about in a scenario of if you are trying to introduce anti-water coning technology? What would be the role of ICDs or passive ICDs or AICD in that case?
Say that front part again. I'm sorry, I didn't hear you.
Well, if we want to introduce anti-water coning technology, say in a vertical well, which is much more coning is much more prominent in a vertical well than in a horizontal well, right? Mm-hmm. Instead of coning, we have a cresting in a horizontal well situations. But if we want to combat and fight, we want to introduce anti-water coning technology. In that case, is any of these ICDs, AICDs, or passive ICDs could help us?
I mean, again, I would say if it's a heavy oil environment, AICDs would help in that situation as well, because they're going to recognize that fluid coming in. And the key is creating those compartments so that you do have some control so the water's not just jumping to the next inlet area, I guess, of the screen or device that you have in there. So the compartments are key to it because you can control that area for whatever length of time. I mean, ultimately in the life of the well, at some point, the water or gas is going to jump across behind in the reservoir. But the idea is to hold that off as long as you can and get the good production you can as early and midway through the life of the well as possible without having to chase that water or gas on the front end as it breaks through early.
Mm-hmm. Thank you.
One question from me, Tony, I'm sorry, but you have to earn your keep.
Yes, sir.
Hey, I didn't hear it, but if you are going to gravel pack a open hole horizontal, can you do your gravel pack and run AICDs or ICDs in conjunction with that system?
Yeah, I know they've done it with ICDs. They did it in Troll with the ICDs. With the AICDs, they have done it on a limited basis with some, they are putting in some materials that will dissolve out, some dissolvable materials that will allow you to get your circulation around to get the alpha and beta waves when you're gravel packing. I'll tell you another study that's out there though, that they ran in the Troll field, is they determined that they did some testing on horizontal open hole gravel packs with AICDs and standalone screen AICDs. And although the gravel packs did hold back a little bit more sand, it was just a marginal amount. So the time, money, and effort that it cost to put in the gravel pack didn't justify the benefit that they got from it. And so that kind of goes back to those trilaterals that they're doing in the Troll field. Because of the ability to really impact the sand control issues they had, they're able to drill these trilaterals with standalone screen and AICDs, and they're not gravel packing any of it.
Awesome. Hey, man, you're welcome to come back. We need your type of expertise here every once in a while.
Hey, listen, I'm happy to participate. I think this is a great organization. This is my third time. Once at my former place, we did a little tour and presentation. And then once in between jobs, I went to one of these things. So, and now I'm here back again. So I'm a big supporter of the group and the organization. I think you guys do a lot of good work.
Thank you so much. Anthony, do you like to be added to our invitee list?
Absolutely.
Okay, I'll add you on for the next presentation that we have, and you can choose whichever one you want to attend.
Great.
But if you do register, try your best to attend it, please.
Absolutely.
Yeah. Okay. So having said that, do we have any other questions to Anthony at the moment?
And before you move into something else,
You take a picture?
yeah, another picture. But Tony, if you can put up a slide that you would like to be in the picture, if everybody turns on their videos as well.
And there is another question out there.
Yeah, I saw that.
From Miguel Barrueta.
Yeah, you're more than welcome to answer the question while you're doing that.
Let's see, let me find a good one.
And the question from Miguel is, how accurate have been the pre-completion simulations versus production allocation with a PLT post job?
Yeah, we've done a really good job. In fact, there's a couple papers written on that. So the prediction models have really done well in proving out the modeling that we've done once we've completed the installation.
Tony, you're welcome to extend on your question if you'd like. I mean, Miguel.
Miguel, are you there?
Yes, that answered my question. Thank you.
Okay, good. Scott, is that the slide you want?
Yeah, let's just use that one. That's kind of a good one, I guess.
Awesome. Yes. Well, if you have combed your hair and you're smiling, here it goes. All right. Thank you. All right. So, Salim.
Thank you so much, Anthony. We appreciate you coming over and making the presentations. We had a number of people, a number of questions that you have received. You can see that there's quite a bit of interest on your topic as well. So without that, now we'll go to our networking session. It's time now about 11:24 at the moment. Actually, today Griffin is not here, so I have to. This is the first time I'm trying it out. What I want to know, if any of you have any preference as to, I think Subhash and Anthony both are here. You let me know to which one you want to go. Actually, you can move from one breakout room to the other one, but you probably have to let me know. Then I will have to move you to that breakout room. But at the beginning, you tell me in which breakout room you want to go. Then I'll try to put you in that breakout room. And if I mess it up, excuse me, because this is the first time I'm doing it. Because Griffin normally does it. He told me that this time he would not be able to do it. But if anyone else wants to help me out with this one, that would be appreciated. Let me try it out, okay?
Yeah, before you do that, Salim,
Mm-hmm.
you know, this, what